Welcome to our lecture video in hydraulics, and in this video we will solve a sample problem using the Hardy-Cross method. So the procedure suggested by Hardy-Cross requires that the flow in each pipe be assumed so that the principle of continuity is satisfied at each junction. A correction to the assumed flow is computed successively for each pipe loop in the network until the correction is reduced to an acceptable value. So this is our target, that the correction be reduced to an acceptable value. So what is the formula for correction? So this is our formula for correction. Alpha, which means the correction, is equal to the negative of the summation of K Q assumed flow raised to n all over n summation of KQ assumed flow raised to n minus 1, where QA is the assumed flow, Q is the true flow. This summation of KQAN is the algebraic sum of the head loss in the circuit, wherein we will assign clockwise as positive. Then we have n summation of KQA raised to n minus 1 as the absolute sum without regard to the direction of flow. So meaning the denominator in this formula will be absolute. So regardless of the flow there, whether it's clockwise or counterclockwise, we will consider this as positive. Whereas in the numerator, we will assign clockwise flow as positive. Now for the value of n, we have n is equal to 2 for Darcy, Westbach, and Mannings, whereas n is equal to 1.85 for Hazen, Williams. Now as for the k values, we have the k for Darcy's as the formula for head loss for Darcy. The K for Manning is the formula for head loss for Manning, and same is true with the Hazen, Williams. So remember that whenever we use the Darcy formula, that means we're using the F, or the friction factor, and then the Mannings we are using the roughness coefficient N, and the Hazen, Williams we're using the coefficient C. So here is our example. So a pipe network shown in the figure represents a spray rinse system. Find the flow in each pipe where C is equal to 120 for all pipes. So this is our starting point. We have a flow Q equal to 0.4 cubic meter per second, and we have an output flow of 0.1 cubic meter per second at points H, G, F, and E. Now we're looking for the value of Q in each pipe here. So we have how many pipes here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pipes. So we're looking for the Q value of the 10 pipes. So how do we solve this? So since we are given the coefficient C here, therefore we're going to use Hazen, Williams formula. So using Hazen, Williams formula, we have our K value equal to 10.67. That would be L. So as we can see here from our formula, so Hazen, Williams K. Then so we're going to use that formula. That is C raised to 1.85 and then D raised to 4.87. Now for the K values of A, these pipes, AB, BC, CD, and GH, FG, and EF, they have the same K value because they have the same length and diameter of pipes. Whereas the pipes DE, CF, BG, and AH will have same K values because they have the same length and diameter of pipes. So we have here our KAB is equal to 10.67. The length here is 600 meters all over 120 raised to 1.85, and the diameter of 0.3 raised to 4.87. .67 times 600 all over 120 raised to 1.85 times 0.3 raised to 4.87. So 320.81. 320.81. And this is equal to K of BC, K of CD, then we have K of EF, K of FG, and same K for GH. There. Next, the K value for AH. These ones here, the 4 pipes. KAH. So that is 10.67 times 400 all over 120 raised to 1.85, diameter of 0.25 raised to 4.87. So that is equal to 519.72. 519.72, and this is also equal to K of BG, K of CF, and K of DE. There. So since we already have our values of K, now we're going to proceed to the correction. The correction to be applied, so correction to be applied, where N is equal to 1.85, and the formula, remember the formula, alpha is equal to summation of K, Q assumed value of Q raised to N all over N, summation of K, Q assumed, and then raised to the power of N minus 1. So since we're using N value of 1.85, therefore the formula becomes negative summation of KQA raised to 1.85 all over 1.85 summation of KQA raised to 1.85 minus 1, or that is 0.85. Okay. So we will solve for the assumed value for the correction, I should say, for the correction here. Now, it will help if we make tabulation for the values of here for the formula for ease of solving. Okay. So here in our table, we have the 10 pipes here, the 10 pipes. Then the key value, so what's our key value a while ago? So the same key value for AB, GH, BC, FG, CD, and then EF. So there is 6 pipes with the same K values of 320. So 320.81. So 320.81. So 320.81. And the rest have the value for K519. So this is the value for the 4 pipes. So that is 519.72. 519.72, 519.72, 519.72. So that's for the K value. Now, next, from this formula, we need to have the assumed value. So we will put here assumed value. How do we do that? How do we put assumed value? We're in here. It's in here, QA. So to put for the assumed value, so let's so for assumed value of flow, or that is QA, we will assign here. So for the direction of flow, since this is the input, so inflow of water, so the arrow will go to the left, and here it will go downward. Then as to this portion here, the water will go to the right, I should say to the right, and then this goes downward, this goes to the right, this goes downward, this goes to the right, downward, and then to the right. So since the inflow is 0.4 and it is divided into 2 flows, so we will assume a value here of 0.2. So take note, this is an assumed value. So either you put here 0.2 here, 0.2, or you can put here 0.3 and then 0.1 here. So it depends on you on what value you will assume, because we still have the correction to be applied at the end. So it's okay whatever value you input, because as it is said, it is an assumed value. So it's okay. So if this is 0.2 input, and then it will split into 2, 0.1 and this one here. So since this is already 0.1, we can put here 0.1, so that it is equal. So the inflow is 0.2, and then the outflow in separate direction is 0.1 and 0.1. So 0.1 plus 0.1 is equal to 0.2. Again, this 0.2 here is going to split into 2. So we will assume that this is 0.1 and then this is also 0.1. And then what will happen here in the junction G is that there is 0.1 and 0.1 water going inside or going into the junction, so that becomes 0.2. Then here there is 2 outflow, so we have here an outflow of 0.1. Therefore, we can say that the outflow here is 0.1. Next, this 0.1 here will split into 2. So we will assume a value here of 0.05. Then let's assume this as 0.05. so there. And then since this is just going to bend here in this corner, so this is 0.05. Then inflow of 0.15, then outflow of 0.1, therefore this is 0.05. Then lastly, we have here 0.05 plus 0.05 equal to 0.1. Therefore, our assumption here is still correct, or that is, there is continuity of flow. So there is balance here. So the inflow here and then the outflow is still correct. So these are our assumed flow. So we will put that in our table. For AB, we have an assumed flow of 0.2 cubic meter per second. For BG, we have 0.1. For GH, we have 0.1. For AH, we have 0.2. For BC, we have 0.1. For CF, we have 0.05. FG, 0.1. CD, 0.05. DE, 0.05. And then EF of 0.05. So these are the assumed values. Next, we will now be able to get the value for K times QA raised to 0.85. So, for all values with 320.81, that is multiplied with 0.2 raised to 0.85. So, that is 81.68. So, that is 81.68. And then raised to the value of 1.85, that is 16.34. Next, we have 320 times 0.1. So, G and BC, so GH, BC, they are the same, and FG, so they are the same. So 0.1 is 0.85. That is 45.32. So that is 45.32 for GH. Next for BC, 45.32, and then for FG, 45.32. Next, raised to the power of 1.85, that is 4.53. Next, the 320 times 0.05. So 0.05, that is 320 times 0.05, CD and EF. So CD and EF. 0.085, that is 25.14. So that is 25.14, 25.14. And raised to the power of 1.85, 1.26. Okay. So next will be the 519.72 times 0.1. So for times 0.1, so there is no similar here. Times 0.1 raised to the power of 0.85. So 73.41. then raised to the power of 1.85, that is 7.34. Next, we have 0.2. So that is 132.33. So 132.33, and then raised to the power of 1.85, that is 26.47. Next, this one here, CF 519.72 times 0.05, same with DE. That is 40.73. Then next, raised to the power of 1.85, that is 2.04. 2.04. Okay, so we have our table. Now let's compute for the correction for loop 1. So at loop 1, what do we mean by loop 1? So this is our loop. This is our first loop. Let's name that as first loop, loop 1. So positive clockwise for loop 2, positive clockwise for loop number 3. So we will now solve for the formula for correction. So for loop 1, so the pipes involved here are AB, BG, GH, and AH. So for alpha number 1, that is equal to the summation. So the summation of, so from the formula, the summation of the KQA raised to 1.85, and we will take as positive all clockwise flow and negative for all counterclockwise flow. So that is equal to negative. So for AB, so for the first loop, we are concerned here for AB, pipe AB, BG, GH, and AH. So for the numerator, we're concerned with the raised to 1.85. So these ones here. Then looking at the flow for AB, the flow of AB is clockwise. So it is clockwise, therefore it is positive. For the flow of BG, that is also clockwise, is positive. Then for the flow of GH, that is opposite the clockwise flow, so that is counterclockwise, negative. And then for AH here, that's also a counterclockwise flow, therefore the sign there is negative. So we will get the summation here of positive 16.34. So positive 16.34 plus 7.34, then minus 4.53, then minus of 26.47. Then for the denominator, so for the denominator we have n, and then the summation of KQA raised to 0.85. So these are the values that we need, and they are all positive. So that is equal to 1. So 1.85 times 81.68 plus 73.41 plus 45.32 plus 132.33. So what's the value for our alpha 1? The first correction at loop number 1. So negative 16.34 plus 7.34 minus 4.53 minus 26.47 all over 1.85 times 81.68 plus 73.41 plus 45.32 plus 132.33. So that is equal to 0.0119. So 0.0119. That's the first correction at loop 1. So at loop number 2. So the second correction, loop number 2, we are concerned with the pipes BC, CF, FG, and BG. So for alpha 2. So the pipes that we're concerned here are BC, CF, FG, and BG. Then looking at the flow, so looking at the flow for BC, that is clockwise, therefore this is positive. For CF, that is clockwise, therefore it's also positive. FG, that is counterclockwise, so negative. And for BG, that is also counterclockwise. If we're looking at this loop, so it means it's countering. So pipe BG, the flow in pipe BG is countering the clockwise flow here at loop number 2. Therefore, we are going to put here negative 7.34. So for those values, we have minus or negative 4.53 plus 2.04 minus 4.53 and then negative or minus 7.34. Next is these values here and this one here. So that is equal to, that is 1.85 times, that is 45.32 plus 40.73 plus 45.32 plus 73.41. So alpha 2 is now equal to 4.53 plus 2.04 minus 4.53 minus 7.34 all over 1.85 times 45.32 plus 40.73 plus 45.32 plus 73.41. So the correction here is 0.014. 0.014. Next, at loop number 3. And the pipes here that we're concerned is CD, DE, EF, and CF. So we have there CD, DE, EF, and then CF. So looking at the flow of CD, that is clockwise, positive. For DE, that is also clockwise, positive. EF is counterclockwise, negative. And CF is counterclockwise with the loop of third loop, so that is negative. Therefore, we're going to use these values for the formula. Loop number 3. Alpha 3 is equal to negative 1.26, positive 2.04, negative 1.26, negative 2.04. Then, for the denominator, that is 1.85 times these 3 here and this one. So, 1.85 times 25.14 plus 40.73 plus 25.14 plus 40.73. So alpha 3 is now equal to negative 1.26 plus 2.04 minus 1.26 minus 2.04 all over 1.85 times 25.14 plus 40.73. Oh, it's already 0. So the value for alpha 3 is 0. Now for the corrected flow, corrected flow. So the 10 pipes, QAB, QBG, QGH. So we're following the pattern here, the arrangement of the pipes here. So that's what we are doing here. So GH, QAH, QBC, QCF, QFG, QCD, QDE, and then QEF. And then the assumed flow, our assumed flow a while ago, that is 0.2, 0.1, 0.1, 0.2 for the AH, BC 0.1, CF is 0.05, FG is 0.01, CD is 0.05, 0.05, and then 0.05. Now for the correction, for the corrected flow, let's look for the correction here in loop number 1. So all pipes for loop number 1 is AB, BG, GH, and AH. So for AB, that is so as we have seen a while ago, the flow there is positive because it is clockwise, so plus 0.0119 equals. For BG, there is 2. We also have BG here in loop number 2. So if you recall, in loop number 1, BG is positive because the flow of BG in loop number 1 is clockwise with respect to the loop 1. Therefore, the correction for the BG, pipe BG here, is positive for loop number 1, while the correction here for loop number 2, since it's countering the flow of the loop number 2, therefore the correction for BG here is negative. So as you can see, what will happen? Correction 1 is 0.0119, correction 2 is 0.014. So what will happen to BG here is positive for loop number 1, then negative for loop number 2. Okay, so that's how our correction for BG is. Next, for GH, if you recall, the GH here is at the bottom. So that is countering the flow of loop number 1. So it is counterclockwise on loop 1. Therefore, the correction that it will receive is minus that is minus 0.0119. So QAH is also counter the flow, that is 0.0119. For BC, we know that BC here is at the top and it's clockwise. It's clockwise. So the correction for BC is positive correction for loop number 2. This one here. So for loop number 2, 0.014. CF. For CF, where is CF located? CF is located here. It is clockwise for loop number 2, counterclockwise for loop number 3. Therefore, when you apply correction for pipe CF, that is positive correction for loop 2 and then negative correction for loop number 3. So what will happen to CF is positive for loop 2 correction minus negative, or that is negative for loop 3 correction. But since we have 0 correction for loop number 3, so there, it's only 0. Next, FG, that is negative because it's countering the flow on loop number 2. For CD, there is positive 0.05. DE, positive 0.0. The correction here on loop number 3 is 0. DE is 0.0. And then QEF is negative of 0 or minus 0. So EF is here. So it's countering the flow here. Therefore, it's negative. So 0.2 plus point, so 0.2119, and that is in cubic meter per second. Next, 0.1 plus 0.0119 minus 0.014, so that is 0.0979. 0.0979. 0.1 minus 0.0119, 0.0881. Next, 0.2 minus 0.119, that is 0.1881. This is 0.114. Then 0.05 plus, that is 0.064. This one here is 0.01 minus 0.014, or 0. Okay, so 0.01 minus 0.014, that is so for FG, let me see, FG is 0.1. Okay, so it should be 0.1. It's not 0.01. So 0.1. So 0.1, 0.086 there. 0.086 cubic meter per second, and this is 0.05, 0.05, and then 0.05. Okay. So these are all in cubic meter per second. So we can put it in here. or if it's done, if it is done, we can write all of these values here in our table. So here is now our final Q. So 21 0.02119. So this is now our, as it says here, the true flow. So for Q as true flow. Zero 0.2119, 0.0979, 0.0881, 0.1881, 0.114, 0.064, 0.086, 0.05, 0.05, and then 0.05. So we have now completed our table. Now, if you want to see for correction, so for continuity, that's why we're going to use this. So this is our flow a while ago. Direction of flow. Now if the value that you get for this, actually we are assuming also the direction of flow. If it turns out that the value for example here in VG, the value here becomes negative, that means our direction is opposite. So you just need to change the direction here and then try to recompute. So the value for AB is 0.2119. So this one here is 0.1881. 1881. This is 0.0979. 0.0881. Then for BC, that is 0.114. For CF, that is 0.064. FG is 0.086. CD is 0.05. This is 0.05 and 0.05. For correction, let's see. If we add this one here, 0.0979 and 0.114, it should equal to 0.219. Okay, so that is correct. 0.2119. So we are preserving the flow as well. Now, according to our handout, so says here, the statement here is, a correction to the assumed flow is computed successively, the word is successively, for each pipe loop in the network until the correction is reduced to an acceptable value. So it means we can actually recompute this one using all these values here. We can again compute for the correction if we are not yet satisfied with the correction. So see here that our correction is just 0.0119 and 0.014. If sometimes the acceptable correction is 0.00, there's 20. If the correction here is 0.0030, that is much better. So we can repeat the process of finding the correction until we reduce the correction to a value that we find as acceptable. So here we have positive clockwise for loop number 1, positive clockwise for loop number 2, positive clockwise for loop number 3. So we can solve them again for the what we call the second cycle. So we can have a second cycle. So let's put the table again. And then same solution. See, we're just going to repeat it. So the values for K a while ago that we got is 320.81 and then 519.72, 320.81, 519.72, 320.81, 519.72, 320.81, 320.81, 519.72, and then 320.89. For our QA, so our QA are the values that you see here in our system. So let's put here QA for AB is 0.2119, 0.0979 for BG, GH is 0.0881, AH is 0.1881, BC is 0.114, CF is 0.064, FG is 0.086, and the last three is 0.05. Then let's get the value for KQA. So 320.81 times 0.2119 raised to 0.85. So that is 85.79. Next we have 0.881. No. 2119 then raised to 1.85, that is 18.18. And then we have 320 times 0.0881 raised to 0.85. So 40.69. So 3.58. Oops, but this should be here. 40.69, 3.58. Next, 320 times 0.114. So 50.65. So 50.65 and then raised to 1.85 is 5.77. Next, we have 320 times 0.086 raised to 0.85, 39.86. And then 1.85, 3.43. So 3.43 for FG. Next, these two here is similar, CD and EF. So that is 0.05 raised to 0.85, 25.14. It is 1.85, so 1.26. Then next we have 519.72 times 0.0979 raised to 0.85, so 72.1. 7.06. So 519 times 1881. 125.6. So 23.63. Point 50.24. And then raised to 1.85. 3.22. And then 519 is to 40.73. 2.04. Okay, so that's our second cycle. Then we solve for the correction at loop 1, that is the pipes AB, BG, GH, and EH. So if you recall, it's the first four. So the first four, AB, BG, GH, EH, and for the flow, for AB, that is clockwise positive, BG is clockwise positive, GH is negative counterclockwise, EH is negative counterclockwise. So alpha 1 is equal to negative 18.18 plus 7.06 minus 3.58 minus 23.63. Then denominator is 1.85 times the values here. So that is 85.79 plus 72.1 plus 40.69 plus 125.6. So what's the value for correction 1 at loop 1? So 3.58 minus 23.63. So 0.0033. Next, at loop number 2, and if you recall, we're concerned with BC, CF, FG, and BG. Then from the flow, we have here the BC has a clockwise flow, positive. CF is positive clockwise. FG is negative counterclockwise. And BG is negative counterclockwise. And all that for the loop number 2. So for loop number 2 is BC, CF, FG, and BG. So alpha 2 is equal to negative 5.77 plus 3.23 plus, negative, minus 3.43 minus 7.06 all over 1.85 times this 50.65 plus 50.24 plus 39.86 plus the BG 72.1. So alpha 2, or correction number 2 is equal to so 0.0038. Next, at loop number 3, and for our loop number 3, so we have, for the loop number 3, we have CD, DE, EF, and the CF. So for the flow, CD is clockwise positive, DE is clockwise positive, FE is negative counterclockwise, CF is negative counterclockwise. Then let's use that in our formula. So for loop number 3, that is CD, DE, EF. So CD, DE, EF, and then that is CF. So alpha 3 is equal to negative 1.26 plus 2.04 minus 1.26 minus 3.22. This is all over 1.85. And then the value of DE here is a CD. 25.14 plus 40.73 plus 25.14 plus 50.24. So we got it from here. And then this one. So alpha 3 is now equal to plus 3.22 there. So 0.0045. The correction here for the third loop is 0.0045. Corrected flow. So for the corrected flow, we have QAB, QBG, QGH, QAH, QBC, QCF, QFG, QCD, QDE, QEF. And the values here for the flow that we corrected: 0.2119, 0.0979, 0.0881, 0.1881, 0.114, 0.064, 0.086, 0.05, 0.05, then 0.05. So for the corrected flow, so as we have seen a while ago, for QAB, that is positive, BG positive, negative, negative for GH and EH. BC is positive, CF is positive, FG is negative, CD is positive, DE is positive, and EF is negative. So the correction for the first loop is 0.0033. So that is plus 0.0033, 0.0033, 0.0033, and 0.0033. Next, QBC. So here are the group for loop number 2, 0.038. So for BC, that is positive 0.038. For CF, that is positive 0.038. QFG is negative 0.038. CD so let's go to the 2. How about BG? BG has 2 corrections. So for loop 1, it's clockwise. For loop number 2, it's counterclockwise. Therefore, we will have a minus 0.0038. Next, so this is equal to now for BC, what is positive? Positive on second loop, 0.0038. So what else? We have CF. Okay, so also let's not forget the CF also has 2 corrections, positive for the loop 2 and then negative for loop number 3. What's the correction for loop 3? 0.0045. So for CF, that is minus 0.0030, or that is 0.0045. So for loop number 3, so positive CD, positive DE, negative for EF, and then for CF. So negative for C. So negative, so positive, positive, negative. And the correction is 0.0045. 0.0045. 0.0045. This 0.0033. 2152. That is in cubic meter per second. Next, 0.079 or 0979 is 0.0033 minus 0.0038. So 0.0974. 0.000881 minus 0.0033. So 0.0848. Then 1848. So 0.114 plus 0.038. It's 0.0038. 0038. So that is 0.1178. Point 0.064 plus 0.0038 minus 0.0045. So 0.063. Next, 0.086 minus 0.0038, 0.0822, 0.0822, 0.05 plus 0.0045, that is 0.545. So 0.545. 0.0545. Next, last 0.05 minus 0.0045. So 0.0455, 0.0455. And all these values is what we're going to put into our table as the true value Q. So that is 0.2152, 0.0974, 0.0848, 0.1848, 0.1178, 0.0633, 0.0822, 0.0545, 0.0545, then 0.0455. Now for correction, for checking, so if we put here, so this is our flow, this is our flow. So this is 0.2152, 0.1848, 0.0974, 0.0848, 0.1178, 0.0633, 0.0822, 0.0545, 0.0545, 0.0455. Checking. So here, the flow here, if we add it, should equal to 0.2152. So 0.0974 plus 0.1178, 2152. Okay. And you can check also the rest. So here, if you add this, it's equivalent to the addition here. So that means 0.0633 plus 0.0822 minus 0.1, that is equal to 0.455. Okay. So this is our Q. So these are the values of Q for each pipes. And this is the tabulated value of Q for all 5 pipes, for all 10 pipes. Okay. So that's all for this video. So for a screenshot here for the example, directions. Corrected value. Then for the second cycle, and then the corrected flow. So that's all for this video.